Today's discussion centers on a recent archive paper introducing NGPT, a normalized transformer architecture. For our expert audience, let's bypass the introductory material and delve directly into the core innovations. What are the key architectural differences between NGPT and traditional transformer models like GPT?
The fundamental difference lies in NGPT's consistent normalization of all vectors throughout the network. Embeddings, MLP outputs, attention matrices, and hidden states are all unit norm normalized. This contrasts sharply with GPT, which employs techniques like RMS norm in specific locations, leading to variable vector norms. This consistent normalization in NGPT fundamentally alters the optimization landscape.
The paper highlights significantly faster convergence. Can you elaborate on the mechanism behind this speedup, focusing on the mathematical underpinnings?
The unit norm constraint transforms matrix vector multiplications into dot products, representing cosine similarities bounded between matical 1 and 1. This inherent boundedness contributes to improved training stability. Furthermore, the update equations in NGPT, using learnable eigen learning rates, AEA and AM, can be interpreted as a variable metric optimization on the hypersphere. Each layer performs a multi-step optimization, moving the token embedding vector along the hypersphere towards the target output. This structured optimization, coupled with the boundedness, likely contributes to the observed faster convergence.
The paper mentions the elimination of weight decay. How does the hyperspherical representation render weight decay unnecessary?
Weight decay is typically used to prevent overfitting by penalizing large weights. In NGPT, the unit norm constraint inherently limits the magnitude of the weights. The optimization happens on the hypersphere's surface, effectively controlling the weight magnitudes implicitly. This eliminates the need for an explicit weight decay term.
The paper introduces learnable eigen learning rates. What is their role in the optimization process, and how do they relate to variable metric optimization?
The eigen learning rates, eigene and ACM, control the step size of the updates from the attention and MLP blocks, respectively. They act as scaling factors, determining the influence of these blocks on the hidden state. This is analogous to variable metric optimization methods, where a matrix, in this case a diagonal matrix defined by the eigen learning rates, scales the gradient before updating the parameters. The learnable nature of these rates allows the network to adapt the optimization strategy based on the data.
The paper presents results showing a 4x to 20x speedup in training steps. However, the per-step computation time is higher for NGPT. How do you reconcile this apparent contradiction?
The increased per-step computation is primarily due to the additional normalization steps. However, the significant reduction in the number of training steps needed to reach a given accuracy more than compensates for this overhead. The paper suggests that further optimization of the normalization operations could further reduce the per-step time, making the overall speedup even more pronounced. Furthermore, the overhead is less significant for larger models.
The analysis of network parameters reveals differences in condition numbers between GPT and NGPT. What insights do these differences provide into the training dynamics?
The significantly higher condition numbers observed in GPT's attention matrices suggest potential rank deficiency and ill conditioning. This could lead to numerical instability and slower convergence. NGPT's consistent normalization mitigates this issue, resulting in better condition matrices and improved training stability.
The paper explores various ablation studies. What were the key findings regarding the learnable scaling factors, Hsieh, Hsieh, Hsieh?
The ablation studies showed that while the learnable per element scaling factors improve performance, simpler alternatives, such as using a single learnable scalar or even fixed values, lead to only minor performance degradation. This suggests that the complexity of the per element scaling might be unnecessary in practice, offering a potential simplification of the architecture.
The paper discusses the relationship between NGPT and Riemannian optimization. Can you elaborate on this connection?
The normalization step in NGPT, which projects the updated hidden state back onto the hypersphere, can be viewed as a retraction step in Riemannian optimization. This ensures that the optimization remains constrained to the hyperspherical manifold. The overall optimization process in NGPT can thus be interpreted as a form of variable metric Riemannian optimization.
The paper concludes by suggesting future research directions. What are some of the most promising avenues for extending this work?
Scaling NGPT to even larger models and datasets is a natural next step. Extending the architecture to encoder-decoder models and exploring its applicability to a wider range of tasks beyond language modeling are also important directions. Investigating the potential for further optimization of the normalization operations to reduce computational overhead is another key area.
Finally, what is the most significant takeaway from this research for practitioners working with transformer models?
The consistent normalization of vectors in NGPT offers a powerful approach to improving training stability and convergence speed in transformer models. The inherent boundedness of the dot products and the interpretability of the eigen learning rates provide valuable insights into the optimization process. While the additional normalization steps introduce some computational overhead, the significant reduction in training time often outweighs this cost. The simplicity of the core idea and the potential for further optimization make NGPT a promising direction for future research and development in the field.
Thank you for this insightful discussion.